Okay, let's define some of the variables that are important to understand for harmonic motion. So we're talking about harmonic motion or simple harmonic motion. And what are the variables? Let's just make a list. I'm trying to think of the right word, but make a list of the various variables. First of all, when we're talking about springs, we are going to talk about spring constant. K for a spring is a spring constant. And maybe we will define that better later. M is of course a mass. These aren't really variables of simple harmonic motion, but when we displace the body from equilibrium, obviously delta x is displacement, and generally we will talk about the displacement from equilibrium, but I do want you to be careful and understand that that defines basically x equals 0 at equilibrium. It doesn't really define that, but we can redefine our coordinate system so that's not necessarily x equals 0, and it makes everything harder, but it is doable. You don't have to define x equals 0 at equilibrium. But so that's for a mass and a spring. But in general, for simple harmonic motion, we've got things like amplitude, right? Amplitude, which is abbreviated, so this is in general for simple harmonic motion, abbreviated A, and the amplitude is the maximum displacement from equilibrium. So what do I mean by that? Hold on a second. From equilibrium. Okay, so for instance, if I take this mass m, and I've already shown it, and I'm sort of doing this motion that you can't see, but I've already shown it being pulled away from equilibrium. If I let go of it from rest, it is going to move upwards, and if there is no friction, it will come back down, but it will never go farther from equilibrium than it is now, right, where I've moved it, where you can see that I've moved it. Highlight there. It's never going to move farther than that. So that's the maximum displacement from equilibrium. So A is that initial delta x. But be careful, because if I move it away a distance delta x, and then I give it some kinetic energy and I push it, doesn't matter whether I push it towards equilibrium or away from equilibrium, next time it comes back, it will move farther from equilibrium, right? Because it had kinetic energy at that point as well. So it's going to move farther from equilibrium. So the amplitude is not necessarily delta x, right? It's going to be the new delta x when it comes back down, but it's the maximum displacement from equilibrium. Now we got to be really careful about this word amplitude, because it is confused. Even in your own textbook, it is really confused and often confusing. Because let's say that as this mass moves up and down, right, what's the word? Words are not coming to me. At some position between equilibrium and its maximum displacement from equilibrium. Let's just pretend that this is, whoops, that was a highlighter, not the pen. Let's pretend that this is the amplitude. That's the maximum displacement from equilibrium. So the mass is just going to move from there to the same distance above and back and forth, right? The mass is going to, if there's no friction, it'll move up and down and up and down. But in, what's the word I'm looking for? In between positions. In between positions, right, here's the mass at some time, and the mass at that point has a displacement from equilibrium, which is a smaller delta x. So that's, right, delta x at some time t, right? And this is delta x max, which is the amplitude. Well, so what often the people, a correct use of amplitude, but a misleading use of amplitude, or is asking what is the amplitude at time t, right? So this is the amplitude at time t. That's not the maximum displacement from equilibrium at all times. It is how far it is from equilibrium at that time. So if you're talking about the amplitude at a certain position or at a certain time, then that just means how far is it from equilibrium at that time, at that position. If you just talk about the amplitude in general, that means the maximum displacement from equilibrium. So there's two different kinds of amplitudes, right? This is a different amplitude. Now, I try to stay away from this one. I try to stay away from the amplitude at time t. Instead of saying what is the amplitude at time t, I would say what is the displacement from equilibrium at time t, so as not to confuse it with the maximum displacement from equilibrium. But you will see amplitude used for a displacement from equilibrium at a particular time. Okay, so that's amplitude. Okay, another variable we talk about is period, right? What is period? Period is equal to, abbreviated as capital T. Oh, and what stupid question. What's the units of amplitude? MKS units are the meter. Okay. Period is abbreviated time T. And what is period? The period is the time for one complete cycle. Time for one complete oscillation. So the period is the time for one complete oscillation. And so that's the amount of time it takes. And it doesn't matter where the oscillation starts, but let's say we start the oscillation here. It's the time that it takes the mass to go up and back down all the way to here. Okay? So if we were to start start the mass at equilibrium and it's got some velocity, right? Hold on. So if we start it here and it's got some velocity, then it's going to go up and come back. And is that one whole period? No, because that's not one complete cycle, right? That's only half a cycle. It's got to go down here and then come back. Now that is one complete cycle. So it's the amount of time for that whole green loop, right? Time for one complete cycle. Doesn't matter where you start. It's not necessarily when it comes back to where it started, but it's got to go through a full cycle. So it might have to come back to where it started twice, depending on where you're measuring the period from. As a matter of fact, if you measure the period from the end points, then it's just got to come back to the end point. But if you measure from anywhere else, it's going to pass that position, right? Anywhere else, it's going to pass that position twice in order to get a full period. Okay, time for one complete cycle. Okay, what about frequency? What is frequency? Frequency is another variable we use to describe harmonic motion. It's abbreviated small f, and frequency is the number of cycles per second. What are the units of period? Going back to units, are the second, right? Period is just a time. Okay, frequency, number of cycles per unit time, number of cycles per unit time. So it doesn't have to be per second because it might be 5 cycles per hour, whatever. 16 cycles per millennium, whatever. Okay, number of cycles per unit time. And you should be able to see, you probably already know, that frequency is 1 over period. If period is period is time per cycle, and frequency is cycles per time, then frequency is just 1 over period. And so frequency has units of 1 over seconds, which is, as you probably know, the hertz, Hz, hertz. It hurts. Okay, frequency. So these are the variables we use to describe harmonic motion and waves. There are 2 other variables you should know about for harmonic motion and waves, and they can be a little bit confusing sometimes, especially because they both generally use the same letter. Angular frequency and angular velocity. Angular frequency and angular velocity are not the same thing, right? Because angular velocity is from rotational motion. If a body rotates, if it goes in a circle, let's just say this is a mass or a car on a track or a runner on a track or whatever, something, or a ball on a string going in a circle, that ball, let's just say it's a ball on a string or a mass on a string, that mass on a string going in a circle is going to pass through a certain angle per unit time, right? And angular velocity is equal to the rate of change of angle, right? Omega is equal to d theta dt. Just like velocity is rate of change of displacement. Angular velocity is just for moving in a circle, rate of change of angle. Whereas angular frequency does not necessarily have anything to do with moving in a circle. Angular frequency is something that comes out of the equations later on, which I'll show you later on, but just recognize that if this mass oscillates with some frequency, then the angular frequency, which is also omega, I know, is 2 pi f. And that comes out of the equations of motion for simple harmonic motion. We'll see why angular frequency is often used instead of frequency, but it's just 2 pi f, 2 pi times the frequency. So we got to be careful about the difference between angular frequency and angular velocity. And in most cases, I'm going to try to stay away from angular velocity and just use angular frequency so as not to confuse. I will not be using angular velocity in this class. I think I can say that with confidence. So these are all our variables that we deal with harmonic motion, and we will now look at the spring and the pendulum and see how they relate to those. I will mention that two more variables that we will deal with when it comes to harmonic motion, when it comes to waves, are wavelength and wave number. But those we don't have to deal with simple harmonic motion. Okie dokie. So last lecture I asked what do you call a fish with no eyes. Now I'll ask what do you call a fish with no legs. That wasn't the least bit funny.